synthetic traffic based on S-based SOC performance verification methodology. Abstract. The SOC use case scenario is becoming more complex, and more than 20 functional IPs such as CPU, GPU, NPU, CMA, CAN, DPU are interoperating to perform on one scenario. If even one IP does not satisfy the performance, the scenario must be modified to downgrade, and spec out or silicon leak speed may occur. Therefore, emulation-based performance verification in pre-silicon stage is becoming increasingly important. For performance verification, PV, we perform a synthetic traffic-based STB-PV using a traffic generator and real traffic-based RTB-PV to operate the RTL IP. Since the IPs ring up to perform the RTB-PV is prepared just right before the RTL freeze. As bug found in the RTB-PV cannot be fixed on time, so it is necessary to respin silicon to fix the bug. In this paper, we propose STB stress test, STB-ST, and STB bus performance test, STB-BP methodology to filter out many bugs at early stage of project. Second, this introduction. Before we introduce our methodology, we would like to define what the SOC performance verification is. SOC PV verified whether all system IPs are designed with the spec performance. 2 is whether all in-bus traffic going through the memory and path that meet the target performance, such as bandwidth, BW, and multiple outstanding MO and latency. And the third is whether the SOC meets the customer's API performance, such as the benchmark score and frame rate of the worst case scenario. SOP PV is proceed to the following 3 steps in consideration of the project schedule and RTL readiness. At the beginning of the project, main system, bus system, and memory source system may only available to run. The system bus and memory bus system are major system backbone IPs that determine the overall performance of the SOC and need to be verified in early stage. The STB-ST verified the system backbone performance by creating various random combination scenarios using the traffic generators. TGs. Once IP integration tests are passed, we start STB-BP to verify the internal system IP such as MMU, security, up-down sizer, and buses. Finally, the functional IPs are ready to enable. We start to generate all IPs factored to each scenarios, and all IPs corresponding to the scenarios are interoperating to the RTB-PV. Because of the project schedule, RTB-PV cannot cover the all real use case scenarios, so only several worst case scenarios are verified. So some bugs are found at this stage, and silicon spin may be required because there is not enough time to fix them. Therefore, it is very important to find bugs in early stages and increase verification coverage. So this paper proposes STB methodology and key component to implement. Figure 1 is the performance verification flow and phase. The section 3 is related research, previous work. This chapter introduces the regions and the problems the RTB-PV must be performed through the related research. RTB-PV film figures the sensor and the display environment and vectors functional IP using RTL in the same way as in the actual silicon, and allow the same traffic and the silicon obtained to be generated as much as possible. For example, if you look at the multimedia scenario below, it shows the process and image sensor to camera subsystem, a video subsystem, and audio subsystem, and a display subsystem to display interface. Figure 2, example of multimedia scenario. The most powerful advantage of RTB-PV is that it is a real traffic. It's a great advantage to be able to preview the same performance as silicon before silicon comes out. Therefore, it is one of the indispensable processes. In order to do the RTB-PV, it is necessary to verify the operation of all other IPs corresponding to the scenarios as well as imaging sensors and all display interface modules. In addition, many of these IPs interact with each other. So the RTP-PB can be started when RTLs matures, and it takes more than 1 month to prepare the scenarios for more than 20 IPs. Therefore, some performance bugs cannot be fixed in time. So even a silicon pre-lisping is required. For performance verification, main bus topology and memory subsystem must be stabilized and verified at the beginning of the project. This is because if the bus topology and memory subsystem are changed, many other IPs are also affected. As we shared before, STB-BP cannot guarantee many test scenarios to cover all corner cases on time. So to break through these problems, we tried to develop the synthetic traffic based on new methodology that verified performance earlier and cover more corner cases. At the end of 2018, STB was the first product, and at that time, the only rise was measured, and the overall operation was verified very slow, and because the TG operation increased wartime clock. Therefore, it was necessary to make an STB more powerful by TG investment that can simulate real traffic and by improving PB workflow. The section 4 is the proposed methodology, and this chapter introduced the STB-PB methodology. The proposed methodology consists of key components, verification, automation, and features of STB-ST-BP. To perform performance verification at the early stage of the time, it's crucial to use the traffic generating performance monitor TGPM for STB-PB, and automation is necessary. The following subsections explain more detail about the features of the STB-BP and explain how to verify the performance of the SOC in early stage of the project with reducing human errors. A. TGPM for synthetic traffic based on STB-PB. Before explaining the proposed TGPM, we would like to show you what important thing to consider when implementing. The connection between the emulator and host Linux machine runtime hosts are connected by PCIe preferred component interconnect express. Therefore, the bandwidth is quite huge enough and is up to the 32 GB per sec as the current emulator, so the bandwidth is not a bottleneck nowadays. But the problem is latency overhead. According to the PCIe specification, 4 GB data read-only transaction only takes less than 1 second. However, it may take more than 5 seconds in real emulation, and depending on the various conditions. One way 4-byte transaction takes 5 to 7 microseconds on PCIe specification, but it may take 14 microseconds at the best on real. Let us do the extreme situation. If the transaction is supposed to read 4 GB from the host Linux and it sends a 4-byte read transaction for 1 GB times. Oh, yes, it's 1 GB times, and it will take over 7 hours. But if the transaction sends 64-byte read transactions, byte read transaction, it will take only around 10 minutes. Therefore, it's necessary to reduce the communication count between the emulator and host Linux machine as less as possible to enhance the emulation speed. To do that, we use the hardware buffer to store the multiple transactions and transmit these at once. In addition, instead of the raw data, hardware processes the raw data to ledger and transmit the ledger only. To meet this requirement, we propose to improve the TGPM for STB-PB. Figure 3 shows the architecture of the proposed TGPM, and the TGPM has two parts, the software part and hardware part. The software part resides on the host side and takes the user's input or gives output to the user. A software part is required for a flexible TG setup and a collecting performance summary. And the hardware part resides on the emulator side. In case of TG, it generates synthetic traffic, which TG puts into test point. And in case of the PM, it calculates the summarized performance result. In this architecture, software and hardware must communicate with each other. So the TGPM has a DPI interface. As described above, it's important to reduce the number of the transactions and while communicating on both sides. So there is a buffer in the hardware part to reduce the number of transactions and maintain the emulation speed. Figure 3 is the traffic generator and performance monitor of STB-BP. One of the core enhancement functions of the TG is to support various traffic patterns. The actual master IP is replaced by a TG, which mimic the traffic pattern of each master IP in the SOC. As shown in Figure 3a, AXI protocol-based TGs can generate a variety of traffic according to user settings such as frequency, target BW, bandwidth, and burst length, and address pattern, and etc. The existing TGs only generate our average bandwidth traffic as shown in Figure 4-A, but it is important to support various traffic patterns to increase accuracy as shown in Figure 4-B and C and D. In our experiment, it is insufficient to use general average bandwidth traffic because as performance test using such a traffic pattern result in no performance problems, but performance test using the traffic patterns as shown in Figure 4-B could result in performance degradation of SOC, which is a performance bug. Therefore, supporting various traffic patterns to increase the coverage of performance verification is one of the most important features in the proposed TG. So another improved feature of the TG is support delay. Some specific IPs such as MMU and LLC are sensitive to address patterns, and using specific patterns in TG settings is not enough or even meaningless for a performance verification. So to overcome this, the proposed TG can generate prepared traffic traces containing address patterns of the actual traffic and enabling more realistic performance verification. So the Figure 4 is various traffic patterns. The PM is a component which gathers performance data at each test point. PM gathers and displays the performance values between the bus and the memory controller. To save word clock cycle time, the hardware PM calculates each PV values in emulation time, and only final performance values calculated in emulator are transferred to the host machine and through the DPI, direct programming interface call, and the call then the values are returned to the file. To reduce the loss of the emulation speed due to the DPI call, and the PM calculate and transmit the result in frame unit, for example 1 microsecond or millisecond, as shown in Figure 3-B, PM transmit the result of the BW MO and the latency in frame units. Using the average, minimum and maximum result in frame units is sufficient and to analyze the performance trend of the SOC and does not degrade the emulation speed. SM, Scenarios Manager Implementation. SM is developed by using synthesizable SV, System Verilog, and DPI interface. It consists of two components, an SM parser and SM controller as shown in Figure 5, and an SM parser configures scenario files based on the user input constraint, in which are usually PV parameters. A user constraint is defined by selecting AMBER AXI bus parameters that affect performance. The values for hardware bandwidth, address patterns, burst length, sizes, and quality of service are selected. Based on selected criteria, a scenario file, which contains scenario descriptors, is automatically generated. Each scenario descriptor has information that is inputted to the SM controller. An SM controller manages all TGs and PMs based on automatically generated scenario descriptors, which configure TG for each master. TG loads computed traffic information that is previously generated by an SM parser and generates traffic patterns accordingly. An SM controller controls TGs by generating command signals to a TGs, while monitoring the status of each TG. The controller shares the verification scenario information in a descriptor such as an expected verification, runtime, and scenario indexes that identify a certain scenario among all scenarios to PM modules. Each PM stores performance information separately based on a scenario indice. On SM controller launched ungenerated verification scenarios, and last, the emulation session is closed. Figure 5 is scenario manager for PV. So all function IPs are connected to their own IPs, such as MMU, security up-down sizer, address remapper, and so on. These system IPs can block the performance of functional IPs due to the insufficient MO, buffer, bandwidth, and long latency. Because those performance bugs are hard to fix by function and metal ECO, and all sub-IPs should verify performance at the early stage STB-BP. Be verified. To verify this, we replace the functional IP by TG at the AXI master port and verify the system IPs are designed to meet the performance requirement such as mean, average, peak, latency, max MO, and max VW. Multiple outstanding and bandwidth. IP-XACT for automation. By the fact that STB-ST and STB-BP handle hundreds of verification targets, TG achieve attachment for each verification point requires a lot of time and effort. It's needless to say about the automation methodology, which can replace the TG for every verification point that we want to verify. When a list of the verification targets were given, the automation methodology searches the verification point from the design, then generated the TG database file for the emulation image build. The TG database file contains detailed information in a short time because it searches the design metadata, which is provided by IP-XACT compared to the design. The IP-XACT has a small amount of data, so the methodology does not require a lot of time to parsing the signal information for TG. As a result, the automation methodology can enhance the productivity. The figure 6 shows that the input and output of the automation methodology. So the first, it leads the list of the verified target, which has the TG attachment point. Second, it searches the TG attachment point and obtains the detailed signal information from the design metadata, which is provided by the IP-XACT. Lastly, the automation methodology generates a TG database file in which describes the TG attachment information. This database file will be used for emulation image build. So the flow 6 is a figure 6 flow of the automation methodology. The D, synthetic traffic based PB, STB-PB. Through the above automation steps, the environmental setup using synthetic traffic becomes possible and various experiments become possible. So test and using synthetic traffic depending on the measurement of DUT and the purpose can be divided into two PV milestones, STB-ST and STB-BP. In the STB-ST stage, the performance of the network on chip and memory controller corresponding to the backbone of the SOC is verified. These blocks determine the main performance of the SOC and perform performance verification on the backbone RTL implemented at a relatively early time. Verify various combination of the paths connected to the backbone bus and perform performance tests using various combinations such as traffic pattern and bandwidth. At this stage, it is necessary to check whether the specification of a SOC product satisfies the required performance. The test the bandwidth, including the target bandwidth and the non-real-time IP of the bandwidth, latency, and DRAM utilization and real-time IP as a whole. Figure 7 shows the diagram when STB-ST is performed in the SOC bus. As introduced above, you can see the TG can generate a synthetic traffic and the PM can measure the performance in which paths are connected in the SOC bus corresponding and to the interconnect of the bus. Several TGs to create various traffic patterns corresponding to the scenario. At this time, this display IP and camera IP corresponding to the real IP must be guaranteed real-time performance, and if the performance is guaranteed, the screen may be disconnected or the frame may be omitted during the camcoding. To ensure these things, there is a QoS that can adjust to the traffic, can adjust to the traffic of the SOC bus, and you can check if this QoS operation operates according to the spec. The priority to guarantee the bandwidth of the IP corresponding to real time can be adjusted. If the service of a specific IP is delayed, an urgent event occurs to increase the priority. Figure 7 is diagram of STB-ST. In the STB-BP stage, the stage test is performed including system IPs at the blocks level following the backbone of the SOC. Since the system IPs are including in time, it can start through the STB-ST stage. The coverage of the DUT is higher because the block level is included. STB-BP includes 6 MMU an up-down sizer, and local bursts that may affect each block performance. During the STB-BP test, we check whether target BW is measured for each path, whether the latency required is satisfied, or whether MO of AXI bus is fully digested. The figure 8, diagram of STB-BP. In mega IP examples as shown in figure 8, each master port goes through many internal buses, MMUs, US, and DS, US or DS, and etc., until it reaches the backbone bus. If TG-PM is attached to each master port by applying STB-BP, the path to the DRAM can be scanned as a whole, so that internal buses, MMUs, and up-down sizer, and etc. can be verified as well. So additionally, TG address patterns are usually set to be general, but if the replay function mentioned previously is used to simulate the IPs with the special address patterns, special traffic patterns and address patterns can be reproduced. So MMU performance can be evaluated through the using hit rate. 5. Result. With the introduction of the STB-BP methodology as above, it has two main effects. First, the very precise test result become possible. The result of the DUT can be directly compared to the specification of the result of the model within an error of less than 5% in performance metric like BW, latency, and MO members as shown in figure 9. So some bugs we found were hierarchy buffer size bug and a long latency issue caused by clocking gating. These were detected by comparing the result of RTL and model, which was not previously easy. Figure 9 is the result of STB-ST. Secondly, PV coverage can be increased due to the effective execution as shown in figure 10. IP-XACT and TG automation enable seamless processes from architecture to RTL development, which can increase the test efficiency. Human error decreased in TG insertion and configuration. The easy TG configuration reduced the time required to configure the scenario. There, in the earlier stage of our SOC RTL design, more test scenarios can be executed and the performance can checked before RTL bridging. 6. Section 6. Conclusion. The proposed PV methodology was applied to the flagship mobile IP-SOC project. More than 2,000 scenario experiments have been completed by STB-ST and STB-BP before RTL bridging, and almost all system performance bugs had been fixed before RTB-PB begins. The automation flow makes it possible to insert 400 TG PM4 building emulation platform and run on another 6,200 scenarios right on time. 2,000 scenarios right on time. We have increased PV coverage using STB scenarios and will enhance the TG to generate more arrest traffic for mimicking the real scenarios in the future. Thank you for your time. Today I read this paper, Synthetic Traffic-Based SOC Performance Verification Methodology. Thank you for your time. See you next time.